Hi friends, welcome to a new session of SolveWorks video tutorial series. This is session number 5.2, assembly exercises with a motion study. In this session we are going to assemble different mechanical machines by giving all degrees of freedom, and we can simulate the motion by using motion study, and also the exploded view and bill of material can be generated. Now let's have a look on the assembly exercises that we are discussing in this session. So this session includes assembly of GENEVA wheel mechanism along with the motion study, a generation of bill of material, and also the exploded view. The second one is cam and follower assembly. Third is bench wise assembly. Fourth one control handle assembly, and the last one is epicyclic gear train. So we'll start with the first one. So we'll start with the first one, a GENEVA wheel mechanism. You can directly go to the assembly platform. Okay, I'm browsing the components. There are 6 components in the GENEVA wheel. I'm starting with the base. Okay, now I'm calling the shaft. Okay, I can join them together by using concentric relation first, and then coincident between these two faces. Okay, for the other part, either we can mirror it or we can continue the same procedure. First, I'm making a replica of this one by press and hold the control button. See, now you can make it concentric. Okay, and then coincident. So the next one is I can call the wheel now. Go to insert component, call the wheel. The same option, I'm making the concentric relation first like this, and now coincident. Okay, this part is fine. Now I'll call the driver. Okay, and making the same options, touch it over the surface. Okay, now so this can independent movement. Now here we can see, and we can restrict the extra degrees of freedom at the time of motion study. Now I am calling the fourth component, that is crank. So the crank should come down to the driver here, see now. And in this particular mechanism we want to the simultaneous rotation of crank and driver. In order to facilitate that, we can check for the axis. In the crank, I'm selecting the top plane, and go to the driver and select the top plane. So we'll make these two planes coincident. So now this will move together only. See, here we can see there is no individual motion because we restricted the motion by using top planes of both of the surfaces. Now I can call the pin, join by concentric, and also here. Okay, here it is. See, once we complete the things, here we can see this is the GENEVA wheel mechanism complete assembly. Now we are going to give the motion study. So the next option is motion study. By using motion study, we can see the real mechanism of GENEVA wheel, and here we can see that when I'm rotating the wheel, it is going inside to the other portion. So we can avoid all these things by giving the contact set. It's also there in the motion study. So we'll start with the motion study in the base. Either you can click on new motion study or you can start directly from here. Okay, I'm going for a basic motion. So first one, I'm selecting basic motion. Now go to the settings. Here you can give the frames. It's up to you. You can go for less frame or more frame, and it will give the smoothness of the animation. I'm giving 30 here. Accuracy is high. 3D contract resolution is also high. Now I'm making it in a suitable position for me to simulate. See, okay, this is fine. Now I'm assigning one motor. We have two kinds of motor, rotary motor and linear motor. Here we need a rotary motor for rotation. For the driver I am giving a rotation, but I'm reversing it. Now we can change the speed. I am making it 20 constant speed, 20 rpm. Okay, and the total 5 second is here. I am making it 10 second. And now we need to simulate the contact of selected components. In order to avoid the contact between the parts, we know that the driver, pin and wheel is making contact between each other, so we need to go to the contact set. I'm selecting the driver and also the wheel, pin, 3 components. Okay, now we can go for the calculation. Here is calculate option. Click on the calculate, which will calculate the motion study. Okay, this is looking perfect now. If there is any error in the motion study or any contact set, that will reflect over here. We can go and rectify it. So this is the final result now we have. Okay, it is perfect with the motion study. Next we will go for the exploded view and bill of material. And the next options are exploded view and bill of material. First I will go with the exploded view. As I discussed in the previous session, we have 2 options, normal and also the radial step. I'm going with the regular step now. Click on the component and there are 3 mutually perpendicular planes, and I'm moving to the Z axis now. Click and moving to Z axis. If you want to move to some other axis, we can click on the axis to move that. So I'm selecting and moving to this way, make it down. Okay, this is the assembly. Now we can give the explode line sketch. I'm selecting the face and this edge here as well. Okay, similarly we can give in the other direction also. Line sketch starting from here to this circle. Okay, that will give the direction of motion. Now once we complete, we can exit the sketch. Now when we go to the assembly, click right button. There is an option for collapse. Click on collapse. That will make the assembly back to the original position. At any point of time we can click on the assembly, right button, go to explode. That will give the exploded view that we have provided. And we can also animate. If you want to know more about exploded view and the exploded animation, you can go to the previous video, that is part 5.1. I'll show you. Go to part 5.1, go directly to the description.
Welcome to a new session of
Go to the description, show more, all the way down. Here the exploded view, click on that. That will explain you in detail about the exploded view of with the animation also. Okay, we are back to our assembly now. Now we can generate the bill of material. As I mentioned in the previous session, generating the bill of material in SolveWorks is very simple task. Click on the bill of material. It is asking for the template. We are going with the BOM standard, that is bill of material standard template. Here you have option for giving the item number and everything, and here you can change the thickness of the border. And okay, click. It is asking for the note area. Click. So it will automatically generate the things. Here we have an option for the description, as I mentioned. So click double click on it and you can enter the description if you need. And if you want to remove the column completely, we can remove it. So I am clicking on the column, delete. Okay, need to select the red button, go to column and delete it. You can make it large. If you want to increase the size, okay, go to, I'm increasing the size now and make it more bold. 26, it's fine. Okay, this will be the final result, and I'm collapsing it so we can keep it. Okay, that's all about Geneva wheel mechanism. Now to the second assembly, cam and follower. Straight away go to the assembly platform of SolidWorks. I'm browsing the components of the cam and follower. I'm starting with the stand. So I'm adding one motor now. So here is the motor. Then concentric relation, and this surface and this surface, so it will be fit over there, and it can rotate also. Now insert component. I'm going to take the support. Okay, making this face coincident with this one. In the other way, and this edge to the back of the support. Now I can, okay, here we have an error that we can fix. In the coincident we need to flip it out. Okay, perfect. Now click on the at any point of time we can come to the coincident that we have given, and we can make the necessary changes. So now it is inside moving, and we can give the restriction. It is actually going into the surface. We can give the restriction also. Now we'll call the cam and follower. I'm calling the cam and follower together. Here is my cam and here is the follower, making concentric relation here. And these two surfaces, it will come over here now. Okay, then it can rotate. Here also concentric and coincident, the surface and here. Perfect. Now we will go for the cam option. Go to mate, go to the mechanical mate, and there is a cam. We need to give the cam path and cam follower. So I'm selecting this as my cam path, and here is the follower. Perfect. One or more cam entities have a radius less than, as this it is showing as an error, but it is not at all an error, because we have a straight surface that will make a line contact with the curved part. It will be okay. Here you can see that when I am moving, it will simulate the same motion, and we can check for any error. See, zoom it. Now it is working perfectly. Okay. So when we are using in the cam follower relation, when we are using a straight path, it is showing an error. But if the line and the tangent relation is perfect, that will not make any error in the final geometry. So now we can provide a motor to the surface. Go to motion study, take a motor, and I'm adding the motor to the surface here, and I'm making a speed of 20. A rotary motor. Okay, now yes, here it is. This is the final result, and it is moving exact to the same distance. Now we'll make the exploded view and bill of material of the assembly. Go to exploded view, and we can select, and we can move to any distance, X direction. Here click on the x-axis and move. So these two can be moved together. Select them together and move it. Okay, here I'm making a small distance. So this is it. I can save the exploded view and collapse it again. This is the exploded view now. Okay, and also go for the bill of material. Click on the bill of material, BOM standard, click notes area. So here it is. Can keep it somewhere near to the figure. Okay, this is my final result. I want to remove the description. Okay, and Okay, so this is the final result now. Next we are going to discuss about the assembly of a bench vise. Here we will also see how to make a sub-assembly to avoid the confusion of multiple parts. Sub-assembly of the bench vise screw can be done directly and saved in a folder. We will call the sub-assembly at the time of main assembly. So first we will start for the bench vise screw assembly. Number 3, 4, 5 and 6, that is the vise, screw, then the handle rod, pin and knob is representing a separate assembly. I'm calling the vise screw here. Now I can call the second component handle rod. Okay, first I'm giving a concentric relation between these two, and the rod should be in the middle, and I'm checking for any planes. So this plane is parallel to the hole, and I can check, yeah, the toe plane is in the middle of the rod also. So we can select these two planes that will come together and that will align the rod in exactly in the center of the screw. Okay, now the motion is restricted. I can call the next component. I'm calling the pin and knob together. Okay, the pin and knob. Now I'm making the knob and okay, concentric relation top to this face. Perfect. One more option, we can go for the okay, and this should be concentric to make a passage of the pin. Now these are concentric. Okay, now the surface, I'm selecting the surface with the edge. Perfect, here it is. So one side is okay, and we can continue the same procedure on the other side, or we can go for the mirroring option. Here I'm preferring the mirroring option. Very simple, we have a top plane. Okay, I'm selecting the top plane and these two components as well. Single click, that will come into the other side. Okay, now I can save this sub-assembly. Save as screw assembly. Okay, now we can go for the main assembly. So I'm closing this one now. Go to new assembly. I'm calling the bench vise. Okay, now I can call the second component sliding jaw. Okay, first I am giving a relation between these two, this face, okay, this face and this face, that will come in the same. Okay, now I want to make this face with this one, not in this way but in the other way. See, okay, now it can move over the surface correctly. Now I want to insert the component. The jaw plate is there, I'm calling the jaw plate. So I'm going to fix the jaw plate over here. Select these two faces together, then here it is, and finally these two faces. So it is perfectly fit over the surface, okay, of the jaw. Then we need to fix it in the vise also. I'm taking a copy of this one. Okay, I'm selecting these two faces, made. Okay, rotate it. So these two faces and these two as well. Done. Now it can move over the surface like this. Now I can call the sub-assembly, insert. I'm calling the sub-assembly here. Okay, perfect. Now making these two things concentric. Okay, make it in the other way, reverse, so it can this face and also the face inside. See, it's perfect now, but we know that we need to restrict some motions, so I'm going to restrict the motions now. First of all, I'm giving a screw relation between these two because it is actually moving over the surface without having any relation. Go to the screw relation. I'm going to mate. Go to screw. Distance I'm giving 4 millimeter. Distance per revolution. Go to the okay. I'm selecting this one also. The mate cannot be solved, but we can go forward. It will be over defined. See, we can check that where it is over defining. Go to the mates. Okay, here we have a coincident relation, so we can remove that relation to make it, because now we are over defining the things. I'm removing this relation. Okay, this one as well. Now there is no more error. We can see that. In order to fix that one, I'm going to select this face and also this face, these two faces, coincident. Okay, now it can move along the surface. Here you can see now it is moving. When I'm rotating this one, it is moving, but still we have one problem, like it is going all the way from here. So we can restrict that one also by using distance limit. As we have discussed in the previous session, distance limit is giving the minimum and maximum distance. So we need to give a distance between minimum and maximum distance between two faces. So I'm selecting these two faces. One face is this and the other face is this one. So in order to know the maximum distance, what I'm doing is, see, the distance between these two is, go to evaluate, take the measuring tape. From this surface to this surface, the total distance is 122.25. But we need to minimize the thickness of this one. So I'm selecting the thickness of this one. It is 44.37. When we are minimizing this 44.37 from 122.25, it is 77.88. So we can give the limit now. Go to assembly, go to mate, go to advanced mates. Distance limit is here. I'm giving 0 between these two faces. Okay, 0 is fine. Then I'm giving 77.88. okay, we can check 77.88 here, 77.88. okay, it is perfectly in the same direction. Click it. Now the assembly is over. We can check. See, when I'm moving to the direction, it will not pass to the other end. See here also. And the flexibility is, when I'm rotating this one, this will go. It here is the motion. So this is actually the realistic assembly. Now we can add a motor for simulating the motion. So go to the motion study, then select motor. I'm selecting one motor over here. Reverse the direction at an RPM of 30. Okay, increase the total time to 20 seconds. Okay, here we go. See, it is showing the realistic motion of a bench vise. And we can also create the bill of material and explorer view, as I discussed in the previous session. And that's all about bench vise assembly. So next is control handle assembly, which is a very simple assembly. Here we can see the easy use of slot mate in the mechanical mate section, and also we can compare the regular method of giving an angle limit with the slot mate, and we can also identify how much time that we can save by using the right proper mate option. Okay, we'll straight away go for the assembly now. I'm calling the first part body. I can call all of the parts together. So here we have 3 parts. I'm calling them together. 1, 2 and 3. Now I'm joining the handle with the base by using concentric relation first, then coincident relation between these two faces. Okay, perfect. Now I can make concentric relation between these two, then the face should be coincident, and also these are the two faces coinciding each other. Okay, now I can make the clip first concentric and also coincident, this face, this one. Perfect. So we have completed the assembly. Still we need to restrict the motion. Here we can see that it is going all the way out and it is rotating, so we need to restrict in between these two. And this is a slot. Here we have a slot, and also the component which is reciprocating in between is a circular component, so we can directly use the slot option under mate. Go to mate. In the mechanical category we have the slot option. Very simple. Simply click on the slot and then select the curve. So here is the curve. In a single click, everything finished. Here you can see that it is properly restricted the motion. Now it is rotating very clearly and all other dimensions. So that symbol is the use of slot. Now we will remove the slot option from here, and we can compare the regular angular limit method for giving the limit. So say for example here, this is a starting point and it can be considered as 0, and this end 90, but we need to reference in these two positions from here to here. And when I am checking the references, we can see that in the body the planes are the references, so no plane is actually making a coincident relation with the center of the circle. And in the handle, okay, the right plane is exactly in the middle. So if we can create a plane by connecting the center and this particular circle, we can give the relations. For that purpose, I am opening the body separately. This will be automatically updated in the assembly if we are making any changes here. I am making an axis here, okay, another axis in the middle. Okay, now we have two axes. Now we can join them by using a plane. So we have a plane right now. Okay, I'm closing, saving it, and it is asking whether it should update it there in the assembly. I'm giving yes. So here we have the plane is here now. Now I'm going with the mate option. Go to advanced angle mate. I'm selecting two planes, selecting this plane and then the right plane. Here it is. So the minimum value, it is asking 0, and the maximum value is 90. We can check the 90 whether it is taking in the right direction or not. Okay, it's perfectly in the correct direction. Click OK. See, now it is also giving the same effect. We can see that in order to establish this relation, we actually use 3 to 4 steps extra. So that is the importance of using the right mechanical and advanced mate. Now we can provide motion to the assembly by using motion study option. Here we can see that the motion is an oscillation rather than the rotation. So first we will go to the motion study and then select a motor. I'm assigning a motor here in the other direction. So now we can go for the, rather than constant speed, we need to select oscillation, and oscillation from 0 degree to 90 degree. Here also we have the same angle. Can reduce the frequency of oscillation. I am making it 0.5. Okay, now we can calculate it. So here it is. Okay, it is reciprocating properly. Okay, now I can repeat it. So that's all about control handle assembly. Next assembly is epicyclic gear train. Before starting this assembly, it is better to review the gear assembly by using gear mate that we have discussed very clearly in the part 5.1 of this video tutorial series. We'll quickly review it. Go to part 5.1 and you can directly take the gear mate option by go to the commands. Under mechanical mates we have the gear mate. Click on the timeline, that will take you to the same place. So here we can see different methods how to make the assembly between two gears, and also how to make a relation, and those kind of things are explained very clearly. So just watch it before proceeding with our assembly. And this is explaining about the full rotation, the mating rotation also. We'll go back to our assembly, starting with a new assembly. First I am browsing the component. I'm starting with the shaft. There is a middle shaft. Now I can call the outer wheel, and I'm joining them by using the mate option. I can make the outer gear exactly in the middle of the shaft by using advanced width option. First it is asking for the width section. This is my width section. Then the tab section. This is the tab reference. It is going exactly in the middle. Okay. Now I can call other component. I'm calling the sun gear here. So the same procedure. First make it concentric. Okay. Now this will touch to the surface by coincident relation. Perfect. Now we can call the third component, that is the planet gear. Here it is. So first I'm making these two faces coincident, so now those two in the same plane. So I want to make it exactly in a mating relation. So for that purpose I already have created axis. Here we can see the axis of the sun gear, and I'm selecting the axis of the planet gear also, and the distance is 45, the center to center distance. Okay, once we fix the distance we can set the mating relation more clear. So I can select the front view or back view for getting a more clear view. So here is view. So I'm rotating this one a little bit so it will be exactly in the middle. Okay, now it's almost fine. We will go for other relations now. See here, what we are going to do is we will give the relations between gears. First I am considering the outer shaft, the axis of the outer shaft. In the 5.1 of this video tutorial series, all gear mate options, we discussed about the outer diameter of the gear. Here we are going to deal with the axis. I'm selecting the axis of the outer wheel and then axis of the sun gear. I'm giving the gear ratio now. Go to mechanical mates, go to gear. Here we can see that I first selected outer wheel, the large one, and the sun gear is the second one. So the ratio is 1:3. Okay, I'm keeping that ratio. Now we can check that also. If I'm rotating this one rotation of the outer wheel will give 3 rotation of the inner. Now we will give the relation between sun and the planet. I'm selecting sun, axis of the sun and axis of the planet. So here the gear ratio is, go to mechanical, take gear, so 1:2 in reverse direction. Okay, here it is. Now we can check the rotation. Okay, it is rotating perfectly now. And if I'm rotating the small wheel also, this will give a, so all the wheels are working perfectly. Now we can go for the other option of giving circular component pattern. I'm selecting this one, and total 3 number required. The outer surface is this. Perfect. So it's done. Now I'm rotating the middle, and also it will work with the outer, and we can rotate the small one also, and all the rotations are there. Now we'll go with the exploded view. First I'm clicking the exploded view and selecting the 3 planetary gears, and I can move to a distance. Now I'm selecting the shaft and also the sun gear. So this is the one. Now we can also generate the bill of material as I discussed. Very simple one. Note area. Okay. Now I can remove the description column, and the numbers are updated here for the formatting, and make it bold. Okay. So this is the assembly of planetary gear. So that's all about assembly exercises in this session. We will see more examples in the coming sessions, the simulation. The next session is SolveWorks simulation, static analysis, where we will see different kinds of analysis, also the optimization. And this is directly relating to FEA, the finite element analysis steps. And thank you so much for the listening. We will see in the next session. Bye bye.